Hello and welcome to Calculus Tutorial. With this video we're going to take a look at higher order derivatives. So that is just essentially taking the derivative over and over and over again. You've done it once, now you will do it twice to find the second derivative, and you can even continue on from there. And then we're going to keep going down the line here. We're going to apply this to motion. What does it mean if you take another derivative for motion? And then as well for function analysis. All right, so first let's take a look at the second derivative. Got a couple examples here, and it starts off nice and easy. So if you want your derivative, here I got a nice polynomial, 5x squared minus 3x plus 8. So we'll take the derivative, y prime. So the derivative is just the power rule. We get 10x minus, and the derivative of negative 3x is 3, and the derivative of 8 is 0. So we call that our first derivative because now we're going to take our second derivative. And so we simply add another dash up at the top. This is y double prime. So the first one is y prime, and the second one is now y double prime. And we simply now take the derivative of what we had left over. So the derivative of 10x is just 10. And the derivative of negative 3 is 0. So that is our second derivative. But you do not have to stop there. You could, if you wanted to, take your third derivative. Running out of room here, but this one's nice and easy. Y triple prime. What if we took the derivative again? So we just take what was left over, the 10. What is the derivative of 10? That's nice and easy. 0. And so hopefully you can see there's no reason to keep doing this. Could we take the fourth derivative? It could look something like this. Start using our Roman numerals. Yes, you could. The fourth derivative would be 0. Could you take the fifth derivative? And sometimes you just put a little 5 up there. Yes, you could. It would be 0 again. No real reason to do that. It's a little pointless. So that's how you take the derivative over and over again. For polynomials, that is nice and easy. Sometimes not so much. Y is equal to cosecant x. We just did this in the previous lesson, at least the first derivative. So hopefully we have the first derivative memorized. The derivative of cosecant x is negative cosecant x times cotangent x. And so now if I want to take the second derivative, things get a little more complicated because now we have a function times another function, which means we have to do the product rule. So we're going to take the derivative of the first, the derivative of negative cosecant. Well, this is simply the derivative of cosecant again. So there's the original negative, but the derivative of cosecant is negative cosecant x times cotangent x. Remember, that is just the derivative of the first times the second. Plus, keep doing your product rule, the derivative of the second. So the derivative of cotangent is negative cosecant squared x times the first, which is another negative cosecant of x. All right, so we got a lot to take a look at here. So first, let's get some negatives in order. 2 negatives make a positive there, and these 2 negatives make a positive there. Cotangent times cotangent, cotangent squared. So that will still be with this cosecant in the front. plus, it looks like. Cosecant squared times cosecant is cosecant cubed. And if you want to factor out a cosecant, you certainly could. But I think that demonstrates the point of how you could do that. Could you take a third derivative? Yes, you most certainly could. That, as you can see, gets fairly complicated. So let's leave it there with the second derivative. All right, one more, a nice easy one. Cosine of x. So this one should be nice and fast. The first derivative, the derivative of cosine is negative sine. So what if we keep going? The second derivative. Oops. Well, the derivative of sine is cosine. But there was that negative in front, so that has to stay. Now, keep going. What is the third derivative? Well, the derivative of cosine is negative sine. But there was that negative in the front to begin with. So now there's two negatives, so that actually became positive. All right, now let's find the fourth derivative. Well, the derivative of sine is just cosine. Well, wait a minute. Isn't that where we started? So now, if I do this again and find the fifth derivative, you would get this one. The sixth derivative, you would get that one. The seventh derivative, you would get that one. And the eighth derivative, you would come back to cosine again. The ninth derivative would put you here. The 10th would put you there. The 11th and the 12th would put you back where you started. So you can see there is definitely a pattern here. So if I asked you for, say, what is the 24th derivative? Okay, well, every 4 it repeats itself. 24 is a multiple of 4. 4, 8, 12, 16, 20, 24. All of those are where we start repeating. That would again get us back to cosine of x. All right, so those are our second derivatives there, and third derivatives, and fourth derivatives. So now we're going to take a look at how that what we just learned can apply to motion. What does this look like for motion? All right, so before I get talking about this word problem here, let's remember what we know about motion so far. Your first function, f, that is position. If you take the derivative of position, that is velocity. What if you do it again? What if you take the second derivative? What does that give you? Hopefully, you can sort of guess. Position, velocity, what's the other physics concept that kind of goes along with those? Acceleration. Okay, so remember, velocity is the change in position with respect to time, which hopefully looks a lot like slope, change in y over change in x. Well, what's the definition of acceleration? It's the change in velocity over the change in time, which again hopefully looks a lot like the slope formula, change in y over the change in x. except this time our y value is this y value right here. So the change in f prime, which is the derivative of f prime, which is f double prime. So velocity is your first derivative, acceleration is your second derivative. So now we got enough information to talk about this Mars rover. So the Mars rover catapults a rock straight up, and the following function models the height of the rock. H at t is equal to negative 1.9 t squared plus 10t plus 2. What is the velocity of the rock after 3 seconds? So I want velocity. Velocity is f prime. So I'm going to take the first derivative, h prime at t. So the derivative, let's see, 2 multiplies the negative 1.9. We get negative 3.8 plus, and the derivative of 10t is just 10. The derivative of 2 is 0. All right, so that is my velocity function. So now I'm simply going to plug in 3. H prime at 3. So you plug that in, you get negative 3.8 times 3 plus 10. Multiply those. So when we multiply these two, negative 3.8 times 3, oops, where's my pen? There we go. 3 times 8 is 24. Put the 2 up here. 3 times 3 is 9, 10, 11. So we get negative 11.4 plus 10, which is negative 1.4. I didn't give you any units. I believe that should have been meters per second is what I made those units come out to be. But as you can see, that is a velocity unit. All right, what is the acceleration of the rock after 3 seconds? So now I want acceleration. So that is going to be taking h, go to h prime, then I keep going because I want acceleration. I go to h double prime. So what is h double prime? So that means I'm taking the derivative of this once more. Again, that's nice and easy. It's just negative 3.8. It's a constant. The acceleration of gravity on Earth is constant, and the acceleration of gravity on Mars is constant. So after 3 seconds, or 10 seconds, or 0 seconds, the acceleration is always the same, meters per second squared. Remember, acceleration has that per second per second. So there we have our acceleration. All right, so that's kind of how this works with motion. You get velocity and then to acceleration. All right, one more thing for us to take a look at. So we've done second derivatives, third derivatives, how it applies to motion. Now what about function analysis? So I'm going to put these 3 graphs back up here. We now know this is position, velocity, and acceleration. When this is f, f prime, f double prime. Okay, so let's start with something we've done before. If a function's derivative is negative, so that means this one is negative right here. A function's derivative is negative. What does that tell us? Well, that tells us the function is decreasing. All right, and of course you could do the same thing with positive if you wanted to. If a function's derivative is positive, that means the function is increasing. I'm hoping that makes some sense. But now we're going to add a new one. what if a function's derivative is decreasing? So a function's derivative, f prime, is decreasing. What do we know? Well, now here's why I like this graphic organizer, because the pattern that we had before still holds. So if you have a decreasing to the right, that means negative. So if I tell you the function's derivative is decreasing, that means to the right must be negative as well. So if a function's derivative is decreasing, that means the second derivative is negative. Now, the first one I'm hoping you can visualize. If a function's derivative is negative, the function is decreasing. But what does the other one look like? The second derivative is negative. That means the function's derivative is decreasing. What does that look like? Well, we're not quite there yet, but let me show you an example. This function here, the upside down parabola, is one example where the function's derivative is decreasing or where the second derivative is negative. So just think about this for a second. Take a look at the slope right here. That slope is positive. Then the function curves up to here. Now the slope is 0. And then the function curves down, and now the slope is negative. So if the slope, the velocity, the derivative is going from a positive number to 0 to a negative number. If you can visualize that, positive numbers to 0 to negative, I'm hoping one word that can come to mind is decreasing. You're going from positive numbers down to negative numbers. They are getting smaller. They are decreasing. And so if your derivative is decreasing, that means your second derivative must be negative. So here is one example of an equation, a function, where the second derivative is negative. And we'll be talking about what properties that has. More importantly, what goes right here. That is the big thing that we are leading up to. What goes right there. All right, hopefully that clears some things up about higher order derivatives.